Let me tell you something that sounds simple and is therefore dangerous. You think you understand atoms. You were told they are tiny balls. You were shown neat pictures in books. You were promised that if you zoom in far enough, reality will finally make sense. That promise is false. Atoms are not small versions of everyday objects. They do not behave like planets, marbles, or machines. And the moment you try to force them into those pictures, everything you believe about matter begins to collapse. In business, I learned this lesson early. When you copy surface logic without understanding structure, you fail slowly, then suddenly. Physics learned the same lesson with atoms. Atoms are not solid. They are not stable in the way you imagine. They are mostly empty, governed by rules that don't care about common sense. And here is the uncomfortable truth. Everything you touch, build, eat, and trust is held together by something that is not really there in the way you think it is. Once you truly understand what atoms are, not the textbook version, but the real one, you can never look at reality the same way again. Because atoms don't just explain matter. They expose how wrong our intuition has always been. If I had to summarize everything I know about physics in one sentence, and I was only allowed one sentence, it would be this. Everything is made of atoms. That sounds simple, almost boring. And because it sounds simple, people assume they already understand it. They don't. Why atoms sound familiar but aren't understood? When people hear the word atom, they usually imagine a tiny solid object, a little ball, maybe with smaller balls circling it, something like a miniature solar system. That picture is not just inaccurate, it's misleading. It sneaks everyday intuition into a place where everyday intuition completely fails. Atoms are not small things behaving like big things. They are fundamentally different kinds of objects, obeying rules that do not resemble the rules of tables, rocks, or planets. The trouble begins when we forget that. The first shocking fact: atoms are mostly empty. Let's start with something concrete. If you take an atom and scale it up so that the nucleus is the size of a marble, the nearest electron would be tens of meters away. In between, almost nothing. No solid substance, no packed material, just space. And yet, when you put your hand on a table, your hand does not pass through it. So already, something strange is happening. Why empty space doesn't mean what you think. People hear empty and imagine nothing. That's the mistake. Empty space in an atom is not empty of effects. It's full of electric fields. It's full of probability. It's full of constraints. The reason your hand doesn't pass through the table is not because atoms are solid objects bumping into each other like billiard balls. It's because of electromagnetic interactions and quantum rules that forbid certain arrangements. The solidity you feel is not solidity in the ordinary sense. It's a kind of organized resistance. Atoms are not miniature machines. Another mistake is thinking atoms are tiny machines with parts that do jobs. Electrons are not little planets. Nuclei are not tiny suns. Nothing is orbiting in the classical sense. Those pictures were early attempts to make sense of something that didn't yet have a proper language. They helped for a while. Then they failed. What electrons actually are, and why that's hard to accept. Electrons are not objects with well-defined positions and paths the way everyday objects are. They are better described as patterns of probability. That doesn't mean we don't know where they are. It means the idea of having a definite location is not always applicable. This is not philosophical. It's experimental. Every attempt to force electrons into behaving like classical objects breaks the predictions. Nature refuses. Why atoms don't collapse. Here's a question people often ask. If electrons are attracted to the nucleus, why don't they just fall in? In classical physics, they would. Atoms would collapse instantly. Matter wouldn't exist. The universe would look nothing like it does. The reason this doesn't happen is not clever engineering. It's that the rules are different. Quantum mechanics does not allow electrons to simply sit wherever they want. There are constraints, not forces in the usual sense, but structural rules. Atoms exist because of those rules. Stability is not obvious. It's miraculous. Once you really understand atoms, you realize something unsettling. Matter does not have to exist the way it does. The fact that atoms are stable is not obvious. It's the result of a delicate balance between principles that have no everyday analogies. Change those rules slightly, and chemistry disappears. Change them more, and matter itself disappears. The world you experience is not inevitable. Why chemistry works at all? Chemistry is possible because atoms can arrange themselves in limited, repeatable ways. Not infinite ways, not arbitrary ways, specific ways. That restriction is what gives rise to molecules, materials, life, and technology. Atoms are not passive building blocks. They are rule-following systems. Why atoms don't explain everything, but they explain enough. Saying everything is made of atoms does not mean atoms explain everything directly. You don't explain love by listing electrons. You don't explain economics by writing wave equations. But atoms set the stage. They determine what is possible and what is impossible. And that's powerful. Why intuition fails so badly here? Our intuition evolved to deal with objects we can throw, eat, or avoid. Atoms live in a regime where size is irrelevant, certainty is limited, and observation changes outcomes. So intuition breaks. That's not a failure of learning. It's a reminder of scale, the most dangerous misunderstanding. The most dangerous misunderstanding about atoms is thinking that once you've memorized a picture, you understand them. Understanding atoms means being comfortable with rules that don't resemble everyday experience. It means accepting that reality is under no obligation to look familiar. Why this discovery changes everything. Once you stop thinking of matter as solid stuff and start thinking of it as structured interactions, everything shifts. Solidity becomes interaction. Stability becomes constraint. Material becomes behavior. The world stops being a collection of things and starts being a collection of relationships. And that is a much stranger and more accurate view of reality. Where this leaves us, atoms are not tiny objects hiding under a microscope. They are the reason the microscope works. They are not the end of explanation. They are the beginning. And once you really understand what atoms are, you stop asking, what is matter made of? You start asking a better question. Why do the rules allow matter to exist at all? They are not little solid balls, not tiny machines, not miniature versions of everyday objects. Now we face the next puzzle, and it's an even stranger one. If atoms are mostly empty space and governed by rules so unlike our everyday experience, why do they stick together at all? Why do atoms form molecules? Why does matter hold together? And why does touching feel so convincing when nothing is really touching? The question everyone asks too quickly. People often say, atoms bond because they want to. That sentence sounds harmless, but it's nonsense. Atoms don't want anything. They don't make decisions. They don't prefer stability. They don't seek balance. They obey rules. And the rules allow and sometimes require certain arrangements. Forces are not little hands pulling things together. Another common picture is this. Atoms have forces that pull them together like invisible hands. This is again a useful image, but it hides the deeper truth. Forces in atomic physics are not causes in the everyday sense. They are descriptions of behavior. We don't say the force causes the atom to bond. We say, given these rules, this configuration has lower energy. That difference matters. Energy is not fuel, it's accounting. When atoms bond, people say energy is released, as if something were burned. But energy is not a substance. It's a number we calculate to keep track of change. A bonded system has less energy than the same atom separated, meaning fewer ways for the system to rearrange itself. That's all. No intention, no preference, just structure. Why electrons matter, but not the way you think. Electrons play a central role in bonding, but not as little glue particles. They are shared patterns. When atoms form a molecule, electrons do not sit neatly on one atom or the other. They become part of a combined system. The molecule is not atom A plus atom B. It is something new. That's why chemistry cannot be reduced to billiard ball collisions. The illusion of contact. Now let's talk about something that feels obvious but isn't. When you touch a table, you are convinced your hand is in contact with it. But at the atomic level, nothing touches. What happens instead is this. The electrons in your hand and the electrons in the table are prevented from occupying the same states. The electromagnetic interaction and quantum constraints create a rapidly increasing resistance to further compression. That resistance is what you feel. Touching is not contact. It is repulsion. Why solidity is a field effect. Solidity is not a property of atoms being hard. Atoms are not hard. Solidity is an emergent effect of electric fields, quantum restrictions, and atomic structure. If those rules were different, solid would not exist as a concept. Why molecules have shapes? Molecules are not randomly shaped. They have specific geometries because only certain arrangements are allowed by the rules governing electrons. These shapes determine material strength, chemical reactivity, biological function. Life itself depends on geometry that arises from rules, not intention. Why bonds are not rigid? Another misconception is that bonds are stiff rods. They aren't. Atoms in molecules vibrate constantly. Bonds stretch, bend, twist. Stability does not mean stillness. It means persistence through motion. Why temperature matters? Temperature is not how hot something feels. It is a measure of average motion. As temperature increases, atomic motion increases. At some point, motion overwhelms the structures that hold atoms together. Solids melt. Liquids boil. Not because bonds break from stress, but because the rules allow new configurations. Why chemistry feels orderly? Chemistry looks neat because the rules are restrictive. Atoms cannot arrange themselves arbitrarily. Only certain structures are allowed, and those structures repeat. Order emerges not from planning, but from limitation. Why intuition keeps betraying us? We keep trying to understand atoms using everyday logic, pushing, pulling, touching. But atoms do not live in that world. They live in a world of constraints, probabilities, and interactions that have no everyday equivalence. That's why explanations feel unsatisfying at first. The real lesson of bonding: atoms do not bond because they like stability. They bond because other arrangements are not allowed. That's a subtle but profound shift in thinking. Nature does not choose the lowest energy state. Nature has no choice. Why this changes how you see matter. Once you understand bonding properly, matter stops feeling like stuff and starts feeling like organized behavior. Materials are not collections of things. They are patterns that persist. Touch is not contact. Solidity is not hardness. Stability is not stillness. Where this leads next: if atoms are rule-following systems and molecules are constrained arrangements, then a new question appears naturally. How do these rules scale up into the world we see? How do atoms become materials? How do patterns become properties? Up to now, atoms may still feel abstract, strange rules, probabilities, empty space, invisible interactions. So a fair question is this: if reality at the atomic level is so weird, why does the world at our level feel so solid, stable, and ordinary? Why don't tables flicker in and out of existence? Why doesn't your hand pass through the wall? Why does matter behave predictably most of the time? The answer is not that atomic weirdness disappears. It's that it averages out. The mistake of expecting atoms to scale up. Simply, people imagine that if you stack enough atoms together, you'll eventually get a small version of everyday matter, as if a table were just a very large atom. That's wrong. The behavior of large collections of atoms is not just a magnified version of atomic behavior. It's a new level of description with its own rules. This is called emergence. Emergence is not magic. Emergence sounds mysterious, but it's not. It simply means that when you have many interacting parts, new patterns appear that are not obvious from looking at one part alone. A single water molecule is not wet. 1 trillion of them are. Wetness is not hidden inside the molecule. It appears only at scale. Why materials have properties, atoms don't? An individual atom has no hardness, no color, no temperature. These are collective properties. Hardness comes from how atoms resist being rearranged. Color comes from how groups of atoms interact with light. Temperature comes from average motion, not individual behavior. Trying to explain these things by pointing at a single atom is like trying to explain traffic by studying one car. Why solids are rigid most of the time? Solids are rigid not because atoms are stiff, but because rearranging them requires changing many interactions at once. To bend a metal bar, you must force billions of atoms into new configurations simultaneously. That costs energy. Rigidity is resistance to reorganization, not lack of motion. Atoms in a solid vibrate constantly. They just don't rearrange easily. Why materials differ so dramatically? Carbon can be soft, graphite, or extremely hard diamond. Same atoms, different arrangements. This alone should convince you that what something is made of is only half the story. How atoms are arranged matters just as much as which atoms you have. Structure is destiny. Why strength is not about atoms holding on. We often say a material is strong because atoms hold together tightly. That phrasing is misleading. Strength is about how difficult it is to rearrange a structure. Some structures allow easy sliding, others lock into place. No intention, no effort. Just geometry and rules. Why cracks spread? When a crack forms in a material, it concentrates stress at its tip. That local concentration overwhelms the atomic arrangements nearby, forcing rearrangement to continue. This is why tiny flaws matter. The atomic rules haven't changed, but the structure has, and structure controls behavior. Why friction exists? Friction feels like a simple force. It isn't. It's the conversion of organized motion into disorganized atomic motion. Surfaces are not smooth. Atoms interlock, rearrange, vibrate, and exchange energy. Nothing is being worn away intentionally. Energy is being redistributed. Why temperature smooths behavior? At higher temperatures, atomic motion increases. That motion allows systems to explore more configurations. As a result, solids soften, liquids flow more easily, reactions speed up. Temperature doesn't add chaos. It adds possibility. Why the world feels classical? At our scale, quantum effects average out. The probabilities become so sharply peaked that behavior appears definite. This is not because quantum mechanics stops working. It's because the numbers get large. Large numbers hide weirdness. Why we can ignore atoms most of the time? Engineering works because collective behavior is predictable. You don't need quantum mechanics to design a bridge. Not because atoms are irrelevant, but because their collective behavior follows simpler rules at scale. This is not ignorance. It's efficiency. Why reductionism has limits. Knowing everything about atoms does not automatically tell you how economies behave, how minds think, or how societies evolve. Each level has its own useful descriptions. Atoms set constraints. They do not write the entire story. The deep lesson of emergence. The universe is not built like a machine, assembled piece by piece. It is layered. Each layer obeys rules consistent with the layer below, but not reducible to it in any simple way. That's why understanding atoms changes everything, yet does not explain everything. Why this should change how you think. Once you understand emergence, you stop looking for single causes. You stop asking, which atom did this? You start asking, what pattern allowed this behavior to appear? That's a more powerful question. Where this leaves us, atoms are strange. Collections of atoms are predictable. Between those two facts lies the world. The stability you trust every day is not a contradiction of atomic weirdness. It is the consequence of it. What remains to be answered? One final question remains. If atoms obey strict rules and patterns emerge from them, why does the universe allow such rules at all? Why these laws? Why this structure? Why this stability? That question takes us beyond atoms and into the limits of explanation. At this point, it's natural to feel that we've gone very far from atoms being tiny things to atoms being rules, patterns, and constraints that give rise to the world. But now we have to ask the most important question of all. Why does this way of understanding atoms change everything? Not just chemistry, not just physics, but how we think about reality itself. The quiet revolution atoms introduced. Before atoms were understood properly, People believed matter was continuous, smooth, divisible forever. Atoms broke that idea. They told us something shocking. Nature has structure all the way down, but not in the way we expected. Reality is not built from solid pieces. It is built from allowed behaviors. That shift from substance to structure is the real revolution. Why atoms destroyed certainty. Atoms taught us that certainty is not fundamental. At the smallest scales, the universe does not tell us exactly what will happen, only what can happen, and with what likelihood. This was not a philosophical choice. It was forced on us by experiment. The universe refused to behave like a clockwork machine, and once that door opened, it never closed again. Why explanation became humbler. Physics used to aim for final answers. Atoms taught us to aim for consistent descriptions instead. We stopped asking, what is it really? And started asking, what rules describe what it does? That may sound like retreat. It isn't. It's maturity. Why this changed science forever? Once scientists accepted that matter is probabilistic, structure matters more than substance, and behavior emerges from rules. Entire fields exploded into existence. Solid-state physics, quantum chemistry, materials science, modern electronics. Your computer exists because we stopped insisting atoms behave intuitively. Why this matters outside laboratories. Even if you never study physics again, the lesson remains useful. Atoms teach us that simple pictures can be dangerously misleading. Deeper understanding often feels less comfortable, not more, and reality does not care how convincing our intuition feels. Those lessons apply everywhere. Why everything is made of atoms is not the point. People often quote that sentence proudly, but the sentence is not impressive. What matters is what follows from it. That matter is not solid. That contact is illusion. That stability is constraint. That the everyday world is an emergent phenomenon. Those ideas change how you see existence. Why reductionism both works and fails. Atoms explain why matter behaves as it does. They do not explain why a poem moves you, why a society forms, or why a thought feels meaningful. And that's not a failure of atomic theory. It's a reminder that explanations live at appropriate levels. Atoms set the stage. They do not perform the play. Why understanding atoms doesn't kill wonder. Some people worry that explaining things makes them less beautiful. That has always seemed backward to me. Understanding atoms doesn't make a flower less impressive. It makes it more astonishing that something governed by abstract rules can organize itself into such complexity. Wonder does not disappear with explanation. It deepens. The final misconception is thinking that discovering atoms gave us certainty. It did the opposite. It showed us that reality is subtle, layered, and resistant to simple stories. And that is a gift. What remains unknown and always will. Even with atoms, fields, and laws, one question remains unanswered. Why these rules? Why this universe and not another? Physics does not answer that question, and pretending it does would be dishonest. Atoms taught us where explanation ends. A quiet conclusion. Atoms are not tiny things hiding beneath reality. They are the rules that allow reality to exist in the first place. They explain why matter holds together, why materials behave as they do, and why the world feels stable without ever becoming simple. Once you truly understand what atoms are, you stop asking for comfort. You start asking for clarity, and that changes everything.